Thanks. Wow. Let's see. Awesome. Can everyone hear me? Great. How about a round of applause for the conference organizers? This has been such a great event. So yeah, I'm going to talk a little bit about metaprogramming in Elixir and elsewhere. So let's go. But to start, a little bit about me. My name is Billy. As Chris said, I'm a software engineer at Frame.io. I first started writing Elixir back in 2016, pretty hobbyist, just, on the side. But since November, I've had the pleasure of being able to write it full time. And also a couple shout outs before I get started. So 4 of my coworkers, Chris, Steve, Zach, and Yuval, all really helped me out putting this together. So I really appreciate it. And then also Chris McCord, many of you may have met him. Many know him as the author of Phoenix, but he also wrote this really interesting book called Metaprogramming Elixir, and it's a big inspiration for this talk. So let's get going. When we talk about metaprogramming in Elixir, we often say something like, don't use macros. And, we say it kind of like this, where we're like, don't do it, but you're gonna. It's very tongue-in-cheek. It's kind of self-deprecating. And I think we say it, because metaprogramming can be a confusing thing. It can feel a little unnecessary. But I also think that metaprogramming can be very useful. And I think depending on the problem you're trying to solve, it can be necessary, but it can also become more understandable if you start to break it down. And that's what I want to do today. I want to do a review of kind of metaprogramming as a higher level concept, talk a little bit, define some things, dive into Elixir, talk about metaprogramming elsewhere, and then hopefully bring it together in some kind of coherent way. So yeah, let's define what metaprogramming is. One of the first definitions I ever heard in a very kind of short way was code that writes code. That's not really untrue, but I think a better way of thinking about it is code that operates on other code. The key things being code as input, code as output. It's this process of writing logic that is kind of doing dynamic stuff with other code. And I think even a better way to understand this is to say, how does metaprogramming work? And the really short answer is just compilers. That's it. That's it. But no, really more, it's metaprogramming is about defining instructions to manipulate the output of some kind of compilation process. And, today we're going to talk a lot about compiled languages, but there is a domain of thinking we could go into about interpreted languages as well, just-in-time compilers. But there are also these 2 broad categories. There is textual substitution, which is this idea of just really static replacement patterns. But then there's also syntactic extension, where you get more programmatic. It's the type of metaprogramming that we see in Elixir called macros and elsewhere too. And to see how this all plays out, I want to start by walking through what compilation looks like at a really high level. And this is based on Elixir's compilation process, but it's pretty generic. So at the very beginning, a compiler is going to go and it's going to scan your program, get some context. And then the very first thing it does to provide meaning to your code is it does this thing called lexing. And so the important thing to remember here is that, when a compiler first starts parsing your code, it's just a long string. It's really meaningless to the compiler program. So to get some meaning, it splits this string into unique tokens, and it's done, keywords and operators, things that your language identify as meaningful items. And some metaprogramming really just operates at this level. In C and Erlang, you have these very kind of pre-processory metaprogramming facilities where you just kind of define a pattern in your token stream and it's just replaced outright. But then we get to parsing. And so this is the next step to kind of provide real meaning to the compiler for what your code is doing and looks like. And so parsing takes that token list and it turns it into something called an abstract syntax tree. It's a data structure that provides full meaning of the actual structure of your code. And it's something that your compiler can eventually traverse and turn into a target. But before that happens, this phase called expansion occurs. And so during this, the compiler is going to recursively traverse your tree. And at various points, it's going to encounter a metaprogramming construct, often called a macro. It can be invoked, and what happens is that ultimate idea is that when a macro is invoked, it's going to output a chunk of AST that is just fully replaced at that point in the AST. And so it's expanded. And we do this recursively until either there's a limit that the compiler set or the AST is fully expanded. And this is where syntactic extension is coming into play. It's how metaprogramming works in Elixir, Lisp, Rust, some other stuff out there. And then finally, the last phase, there's really a lot more that goes on here that we're not going to talk about, but we turn our code into some kind of target. So congrats, you know what metaprogramming is. That's it. But let's kind of talk about more what it looks like in the actual languages we use. So we're going to start with Elixir. I use the term macros. That is what we call metaprogramming in Elixir, the main facility we use to do it. And macros look very similar to functions. In Elixir, they're defined very similarly to functions, and we do so, alongside our other code. And we invoke them essentially just like functions. But the key difference is that functions are operating at runtime. Data is flowing through our programs, functions are being invoked and manipulating data structures, whereas macros are invoked once at compilation. And again, the fundamental operating element is the abstract syntax tree. And as I said, it's this data structure the compiler has produced that represents the structure of our code. But the really cool thing about, the way this works in Elixir is our AST is written in these native Elixir data structures. It's very easy for us to interface with it and operate on it just like any other data structure in our programs. And this is what it looks like. It's always this simple 3-element tuple. The first element is the name of a function or a macro, something that can be invoked in the form of an atom. The second element is this list of context that the compiler has gotten. And I'm not really going to talk that much about the second element because it's not super meaningful for this talk. And then the last element is this list of arguments that the idea is they're to be passed into the function identified in the first. So I want to take a look at a very simple version of this. This is a very simple operation using the infix addition operator, 1 plus 1. And this is what the AST for that operation looks like. We start with this, the atom representation of the plus operator. It's a function. We have some context, and then we have our 2 arguments. So we have the basic understanding here of how the AST works. And so the next thing I want to talk about is the 3 major building blocks we use to write macros in Elixir. And they are quote, unquote, and defmacro. So first, quote. We use quote to generate the AST representation of any chunk of Elixir code whenever we want. This is actually literally how I have gotten all the examples for this talk. But we can, 1 plus 1 is simple. We could pass anything in. Here's something a little more in depth. This is the end result here. We have something that's a little more complicated, but we can break it down. It's not that hard. You have you have def, that call to define a function. We give our function the name add, and we have 2 arguments. And then we do some logic. In this case, we're just wrapping addition via the infix addition operator. Next up, unquote. So this is the opposite. It's, or not the opposite, but it's kind of the inverse. It's used for interpolation. Very similar to string interpolation if you've ever done it. You have this ability to just inject values into the AST you're generating. So let's look at something you don't want to do, or maybe something that isn't going to work the way you expect. You have a value assigned to a variable outside the block of your quote, and you want to inject it in, and this is what's going to happen here. In the second case, we have this count variable just being interpreted as a literal. And instead, when we use unquote, we get this ability to inject the value in. And finally, I want to take a look at like how we actually bring this all together to write a macro. And you know, I want to just have like 2 key goals for this example. It's pretty simple at its face, but the things I'm trying to show here is 1, doing something like transforming the AST in a way that you really couldn't do via a normal function. In this case, we're going to inject some new code, a function definition. And then the other thing is like the ability to very easily work with the AST as a data structure. So I have this macro called cache op, and it's a little big, so I want to break it down. So we have this definition. It's taking in a single argument as an AST. It's expecting it to be some kind of like functional operation, a function call. And I'm also doing this thing where I'm like pattern matching against the AST. I'm pulling out the name of the function, some arguments. Then we output this whole quote block. Again, like as I said a little bit earlier, your macro is expected to kind of output a whole valid AST chunk that can be put in place in the AST, the larger AST data structure. And so that's what quote's going to do here. We're doing one thing at its core. We're defining a function called doop, and it's going to do 2 things. 1, I'm going to generate a little kind of like metadata string describing the operation I'm about to perform. And then I fully just interpolate the whole AST. And this is actually just going to like perform the full operation that was passed in. And so we can imagine how we'd use it. We have this demo module. We bring in our macros, functions. We have the macro cache op, we call it. And now we see the demo module has this function doop that we can call, and we get both the string and then we get the result. And we can also like imagine or visualize what the compiler is doing here. We have this call to cache op, and in reality, when the compilation process is done, what our file really looks like is this. We just have this new function in place to where what we actually wrote. So I hope for those who have not spent a lot of time writing macros, y'all have like a more solid understanding of like the fundamentals of it. But there's also kind of this larger question of like, why even do this? And I can't speak to it all. I think that there's like a lot of thoughts around when it's good and when it's not, and I'm going to speak to it a little bit more later. But I think first here for like Elixir specifically, there are like 2 really interesting use cases I personally see a lot in the work I've been doing, which is code reuse and this idea of language creation. So by code reuse, another way to think of it is this idea of like injection instead of inheritance. So if you come from an object-oriented language, or you've ever written in an object-oriented language, you may have encountered a case like this where you have a base class with a method, and then you want other subclasses to inherit from it and have this like shared functionality via the methods on the base class. But in Elixir, we're living in this functional world. It's magic, it's lovely, but we don't have classes, we don't have methods or objects. So instead, we have this thing called the using construct, where we could define a macro with this double underscore called using. And if we call the use keyword in any other module, all the logic, that macro will be invoked. And we often use this to like inject shared functionality. And you could imagine, instead of writing this one like get name function, I'm writing like 20 and just like really reducing repetitiveness. And then again, like now demo has this special little shared function. I think something a little more kind of understandable and something we use a lot in Elixir is for language creation, specifically DSLs. I'm sure if anyone has used Phoenix here, you've encountered the Ecto library for managing data. And so the Ecto schema module allows us to define schemas to map to database tables. And we have this DSL via a bunch of macros. We have the schema macro, we have the field macro, and we have this very declarative way of describing the shape of our database structure, and it's very visible immediately. But then also on this module, Ecto is, the macros are abstracting away a lot of really interesting logic for us. We get implicitly a struct that's been defined on user. And then Ecto itself defines all these like hidden helper functions that are used for generating queries. And this second bit about language creation, I think, is really fundamental because it gets at something which is that macros are the nature of Elixir. And what I mean by that is kind of what these phrases are getting at. So a lot of times people will say like Elixir is a language of macros, or it's a small language. I've also heard Elixir is an Erlang preprocessor. What people are getting at is that much of Elixir is actually just macros. And so let's take a look. Def. You may think of def as like defining a function. Def is a keyword. It's not. It's really not. It's a macro. And we can see this when we look again at the AST of it. We have this first element here, def. It's indicating to our compiler, it's invocable. And another way we can see this is if we break def down a bit. So all four of these definitions of the add function are fully valid syntactically. At the very top one, which is what we'd write a lot, we have all this syntactic sugar and all this helpful stuff that Elixir gives us. We have the omission of parentheses and do end blocks. But at the bottom, we're invoking it much more like a literal function because really it's a macro. It's functional. It can be invoked. And this is all over the place. All of these operators and things that we think of as keywords are macros in Elixir. And this is not an exhaustive list. I just put this together pretty quickly. So, in the end, we get this thing where Elixir is this pretty small core and has this really interesting rich layer, this standard library of macros built on top of it. And I think it's interesting, once you kind of understand this, you could start to shift your thinking about the way we're writing code in this language. A lot of times our code is really just compile time instruction to generate other code or to kind of manipulate the compilation process. And we have this ability to pretty easily extend it further because we have these constructs that are fairly accessible to us. And so with that, I want to move to this language called Lisp. You may have heard of it because it's in the title of this talk. But I want to talk about Lisp because a lot of these ideas that I've just talked about in Elixir come from Lisp. And so a little bit about it very quickly. Ancient language compared to Elixir. Originally specified back in 1958. It's actually pretty incredible. It was, I believe, the first dynamic programming language, So anyway, a lot of interesting influence it's had, but it's actually this family of dialects. There have been many different directions it's gone, and a lot of them have powerful macro systems of their own. But across all versions of Lisp, there is this unifying concept of homoiconicity. Wikipedia tells me that homoiconicity is the extent to which code itself is representative of the internal program structure. So, I don't know. That's a lot of words. I think there's an easier way to explain this, and it's really two pieces. One, you have code that is often, or that can be viewed as a data structure itself, and that data structure is basically just an AST. And in Lisp, we get this in the form of what are called S expressions. There are these parentheses-bound linked lists, and the elements within are separated by spaces. This is an example of an S expression in Lisp to do addition via the plus operator. And we can immediately see right away the similarity between the S expression in Lisp and the Elixir AST. And Lisp is heavily metaprogramming oriented, and there have been a lot of kind of different directions it's gone. Common Lisp gave us the defmacro keyword. The scheme family gave us this concept of hygiene, which I don't really have time to talk about, but it's cool. I want to focus today specifically on an example from this language called Racket as a comparison because its macros in Racket are very different. So Racket is part of the scheme family, and you can do a lot of stuff with macros. You can match against an AST or a stream of tokens. You can use these special match shortcuts, and you have this ability to like separate your macros into phases of invocation. Here's a quick comparative example of two identical macros, one in Elixir, one in Scheme or Racket. And it's really simple. It's just taking a value, it's expecting it to be some kind of integer and incrementing it. So the key difference is like you have to be more verbose about defining your macro in Racket. You have to not only define kind of the name and the pattern, but you have to explicitly match against the data coming into it. And then you have to give cases like this is what I think the AST is going to look like. And in this case, we're just giving it one case. And then we have an output. So I asked this question in my talk title. I kind of regret doing it in the title. But anyway, is Elixir just a Lisp? The answer is no. It is not. Why is that? Well, the reason it's an abstraction. That's the reason. You know, Elixir is not homoiconic. It has this layer of abstraction above Lisp. If you want to think about writing code in Lisp as writing in AST, then you can think about writing code in Elixir as writing other code that writes the AST for you. And, you know, I think we get some benefits out of this. We have this ability to, you know, work with a system that's maybe a little easier to understand, especially to newcomers, and it can provide a different way of structuring our code. But, you know, also Lisp has this metaprogramming system that takes different forms. But again, Lisp, it's heavily influenced Elixir. It's given us a lot of the design of our macro system. But I think like the really key thing, the comparison is this like easy access to these compiler artifacts, whether it's the fact that you're writing code that already is essentially what your compiler is working with, or you have the ability to generate compiler data structures. It makes it easy to think about manipulating compilation. So before I pivot, or before I go to the conclusion of this talk, I want to pivot once more. And I want to talk about thinking about metaprogramming in another language. You may have heard of it. It's called JavaScript. You know, I think people have a lot of opinions about JavaScript. Personally, I actually really like the language, partially because I wrote it for a while, or a long time before moving into the Elixir world. But I want to talk about JavaScript because I would argue that modern JavaScript relies on metaprogramming just as heavily as Elixir does. And to unpack why I think that, it starts with the fact that the JavaScript ecosystem is flourishing right now. You know, we've started with this specification for this interpreted dynamic programming language. We have a bunch of different runtimes. We have Node on the server, browsers, and then we have like build tools, things like TypeScript. We have all these really rich frameworks, and it's in these last two areas that we see like metaprogramming patterns. They're starting to emerge, or they're even fully ascendant. And I'm going to focus specifically on this build step that we call transpilation in JavaScript. And what that looks like is this. You're writing JavaScript, you have your code base, you're likely using the most recent form of the language, doing really modern stuff, using modern tooling. But your code needs to run on a bunch of different destinations, browsers that may be using older versions of your language. And so you do this pre-processing step to convert newer JavaScript into backwards compatible JavaScript. And the thing is, it's just a compiler. It's compilation. We're not necessarily converting our JavaScript from, you know, JavaScript to some low-level language. But if you like think about transpilation, it's all about parsing, lexing, creating some kind of data structure that the program can traverse and convert into other JavaScript. The premier transpilation system in JavaScript is Babel, and it's driven by these compilation extensions called plugins. And like a very quick example of one is you have this like module export to make a variable or a function accessible outside of your file. This is not valid or interpretable by various JavaScript browsers or runtimes. So you could translate it into something like this. This is like what the default output is from the default Babel configuration. And the thing is, Babel plugins really are a metaprogramming facility. They are invoked during Babel's compilation stage or the transformation stage of the compiler when it's kind of like parsing and expanding its AST. And if you look at Babel plugin code, which in hindsight I probably should have included a quick example, but Babel plugins, they operate on these AST chunks. It's very similar to the way macros look in Elixir, but they're really not macros. And the key reason is that, this doesn't live alongside our runtime code. It's happening separately and often done by like these third-party libraries that we might not really have a lot of clarity into. So again, like via Transpilation, we have a compilation step and you can metaprogram it. And we often do in the form of these extensions for our transpilers. But I also think these patterns exist in other parts of the JavaScript universe. Two very quick shouts. One, the Svelte framework developed by Rich Harris. You see the fact that the framework itself is called a compiler, and it has these like special syntax annotations that inject reactive functionality into your components. And then the React hooks model of having these like declarative behavior injections into functional components. So I'm going to start bringing things together now. And I want to start with a bit of a recap of some of the stuff I've talked about. So at its most simple, metaprogramming, it's just programmatically modifying the structure of your code. And we do this via some form of compilation time programming. And it can often be another way of abstracting logic. And even where appropriate, it's possible to extend the behavior of the languages we write. I think it's pretty clear that when we understand metaprogramming patterns, it becomes a little easier to talk about it, to read it. But I also think, again, like metaprogramming provides this additional lens for thinking about just software. The really key thing being like the division between logic that happens during compilation and logic that happens at runtime. And I think we can like really provide this, or you can use it as a way of thinking differently about like build tools and type systems and framework runtimes. And that's all well and good, but like, why do this? I think like I've spoken to it a little bit, but I think there's definitely a lot more discussion about the merits of like how much you can do and how often you should be using metaprogramming. And it's a hard question to answer. I think the quick answer is like lean on the community best practice. Maybe that's a bit of a cop-out. I don't know. But like in Lisp, like the practice is kind of like to do it all the time. There are some people in the Lisp world who would say that almost all of your code should be compile time instruction, and that you should be like doing very little runtime code and using these really esoteric custom-built DSLs. That can be maddening. In Elixir, we're more like this, just like metaprogram, but do it carefully. And hopefully we can all be, a little bit less defensive about it and like a little easier or a little more aware of how to be careful about it. I think a better question to ask, or something that I feel more able to answer after giving this talk, is like, when does metaprogramming feel like a good option? And, like why do we see it more frequently in Elixir and Lisp than we do elsewhere? Why does it feel less kind of like magical and easier to peel apart in things like Elixir and Lisp? And I think it comes down to these two categories. So the first is expressiveness. It's like, how programmatic can you actually be? How much control do you have? And can you do it in a way that feels like natural to the way you're writing your code? And the other is this idea of opacity. How accessible are your metaprogramming constructs? Does it feel like a black box? Does it feel like magic? Or does it feel like a layer you can easily pull away? And I think we can even plot this on a matrix. So let's do it. I would argue JavaScript is down in this bottom right quadrant. It's pretty expressive, but it's really opaque. It's hidden away. We are, again, like compiler configuration is often totally separate from our runtime code bases in JavaScript. C, Erlang, other languages with like very kind of like static textual replacement. Pretty expressive, or not that expressive, but not that opaque. Like It's very visible. It's part of your code base. It lives along your runtime code. And then we have this. We have Elixir, Lisp, and a language I didn't talk about, but I think it lives up in this upper right, Rust. It's these languages where you have this like highly expressive, pretty low opacity system, something that's visible and easy to use. And I would argue that like this is where metaprogramming starts to feel interesting, and this is languages where we start to kind of see it used more often. And I think it's also a really interesting exercise to think about, like, maybe let's bring another language up into this upper right. It might not be JavaScript, but JavaScript has so many different like compilation pipelines, and a lot of activity is happening and thinking about like bringing the language forward. I mean, it could be really interesting to think about how to add an idea of a macro to JavaScript, or if you're writing your own compilation system or just a parser, anything that has like compiler logic to it, could be interesting to think about how you would actually make it programmable. And regardless of how much you want to use this, or like how much you want to like tackle metaprogramming, I hope that at the end, like, this makes it a little less kind of black boxy, a little more easy to grok, and that whatever the result, you're able to go forward and metaprogram with a little more confidence. Thanks. One question? Yeah. I didn't. So before I proposed this talk, I knew very little about actual Lisp, and it's just there is so much in the Lisp world, and so I focused on like languages that have a little more of an established community. So I focused primarily on Common Lisp and Scheme via Racket, and just spent a lot of time looking at that. So if you want to talk about some of that stuff, come find me after or at the after party. Cool. Thank you.